See, most people have a nice review week. That's good to hear. So, let me see here. First things first, okay, so I'm just recovering from COVID. I'm still in isolation. So if I stop the class or at some point or something, it's just because I'm still not 100%, okay? So just bear with me. This is the first that I'm going to be speaking for more than a few minutes, so hopefully everything will go all right, okay? We are going to start today with the exercise 4.18 that involves transient processes, okay? I suppose you covered that already, so I'm just going to start straight into it. Can everybody see it properly? The screen? Sorry as well, because I'm not using my normal Wacom, so I'm using a different device that I had at home. So hopefully I won't have problems with the technology as well. Oh, a 5mm thick. So I start taking out the data of this one, okay? My thickness, oops, thickness is 5mm. Stainless steel, so you also know the material. And we know that's a strip, okay? So it's something very thin. We have the image already in there. Sorry. What else? And we are given the conductivity of the stainless steel, 21 watts per meter Kelvin, and the density, 8,000 kilograms per cubic meter, and the specific heat capacity at constant pressure, CP, 570 joules per kilogram Kelvin. Okay. Moves through a furnace at a speed of 1 centimeter per second. I have one more information here. My speed, my velocity, sorry, 1 centimeter per second, or we can say that's 0.01 meters per second. And it's being heat treated as it moves through a furnace. So we're talking here about a heat treatment. You saw that in materials with Mora that we can have some types of heat treatment, okay? So this is a type of heat treatment that occurs in a furnace where we pass a stainless steel through a furnace. And the furnace is maintained at 900 degrees Celsius. With a convection heat transfer coefficient, so my heat transfer coefficient due to convection is 80 watts per meter square Kelvin. If the furnace length is 3 meters, so I know that the length of the furnace 3 meters, okay? So from here to here I have 3 meters. And stainless steel enters at 20 degrees Celsius, so I'm saying that the temperature initial of my surface is 20 degrees Celsius. I want to know what's the temperature of the stainless steel as it leaves the furnace, okay? I'm going to say that I want to know my temperature at a certain certain point in time after a few seconds that it passed through the furnace, okay? Well, we have a strip, stainless steel. Okay? And as this strip is passing inside our system, I have an area in the top and an area in the bottom that are subject to this heat transfer, okay? So my heat transfer is occurring in the top and in the bottom, okay? So I can see that I have two areas, two side areas subject to this heat transfer. What we want here, okay? First of all, some assumptions, okay? We are talking about transient heat transfer, okay? But we are going to assume that our thermal properties are going to remain constant. I'm going to assume that my heat transfer coefficient is uniform on my surface. I don't have any information about radiation, okay? So I'm going to consider here that there is no radiation, that my radiation. One important thing, when I talk about transient heat transfer, you probably studied one thing called the lump capacitance method, okay? Lumped system analysis. But we just can apply the lump capacitance system, the lump system analysis, if certain condition is met. It just can be applied if my Biot number is lower than 0.1. So before we start solving our problem, we are going to see if you actually can use the lump capacitance analysis for this transient problem, okay? So first part of the problem, we established that it is a transient problem. So I have an initial and a final time. So my strip passes through the furnace with a velocity. That implies that there is a time involved, okay? And I want to know the temperature when it leaves the furnace. So it will leave the furnace after a certain time. How do you find the Biot number? What's the equation for the Biot number? My Biot number is equal age of convection, specific length divided by my conductivity. I don't have my specific length, so the first thing I started doing this problem is to find my specific length. So my first step here is find LC. Well, if we go to the book, 5th edition, the one that I mentioned the other day, page 240, we have the equation for the characteristic length, not specific length, sorry. For the characteristic length, my characteristic length is equal volume divided by my superficial area where my heat transfer is occurring. I know that volume is my thickness multiplied by my area, correct? And let's look at our area. I have an area in the top of my system and the bottom of my system. As it's a very thin thing, I'm told that it's a strip. I'm not going to consider the side areas here, okay? Just the top area and the bottom area. So I can say that I have twice my area, right? And this is my thickness. Well, thickness multiplied by area is volume. Twice my area is the area of heat transfer. I can cancel area with area. So my characteristic length in this specific case is going to be my thickness divided by 2. So my characteristic length for this specific case is going to be 5 millimeters. That's my thickness divided by 2. That is 2.5 millimeters, or 2.5 times 10 in the minus 3 meters. Okay. First thing, we found my characteristic length applying the bio equation. I don't know if you say biot or bio in English, but this equation here comes from the book, is equation 4.9, in case you want to check in the book, okay? Now we're going to find my Biot number. Biot number is equal age of convection, characteristic length divided by my conductivity of the stainless steel. So my age of convection was given already, that is 8, and was also given the stainless steel K. Okay, so I have everything that I need. So my age of convection, see, is a bit trickier to use. So 18 watts per meter square Kelvin multiplied by 2.5 times 10 to the minus 3 meters divided by K of the stainless steel, 21 watts per meter Kelvin. So my Biot number 0.00952. This number is lower than 0.1, therefore I can use my lump capacitance, my lump analysis, okay? Lumped system analysis. So you heard the word transient, or you saw something that changes with time, or that a change with time is implied. First thing you do is check if you can apply your lump system analysis, okay? Well, since we can apply the lump system analysis, the first thing we need to find is the value for B, okay, the constant B. So B is equal age of the surface divided by rho Cp volume. Okay. I know that the relationship between area and volume is equal to my characteristic length, so I can rewrite that. Age of convection is equal rho Cp characteristic length. And I have everything that I need again. If you want to know which equation this one is, you can look in your book. This is equation 4.5. Okay? Equation 4.5 from the book. So 80 watts per meter square Kelvin divided by 8,000 kilograms per cubic meter, 570 joules per kilogram Kelvin, 2.5 times 10 to the minus 3 meters. So our value for B, 0.00718 second in the minus 1. Everything all right so far? Any questions? Checking the chat here. No questions. Moving on. The next thing we need to find is the time. Well, we know that it is transient. We need to find how much time is involved in my system. Find the time that the stainless strip takes to pass through the system, okay? Well, my time is going to be, I know the length of the furnace, and I know my velocity. Okay, so if my furnace is 3 meters long and my velocity is 0.01 meters per second, my strip is going to take 300 seconds to move through the furnace. So my heat treatment takes 300 seconds. So I'm heat treating this stainless steel during 300 seconds inside this furnace. Well, now we can apply the equation 4.4 from the book that tells us that my temperature at a certain time minus my temperature of the air divided by my temperature of the surface at the beginning of the process minus temperature of the air is equal to E in the power of the B minus B multiplied by my time. So what I want to find is the temperature at the time T, my temperature at 300 seconds. That's going to be my temperature of the air plus temperature of the surface at my initial time minus temperature of the air multiplied by E minus B multiplied by my time. Notice that the unit of my B is second in the minus one. Unit of time, second. So when I multiply one by the other in this part here, they are going to cancel each other, okay? That's how I'm going to end up with just a unit for temperature. So my temperature at my time T is going to be my temperature initial, my temperature of the air. So I'm saying that my systems, my heat treatment is happening at 900 degrees Celsius, plus my initial temperature of the strip, 20 degrees Celsius, minus my temperature of the air, 900 degrees Celsius, minus my value for B. We found it to be 0.007018, 0.007018, second minus 1, divided by 300. Sorry here, 100. Well, if we solve that, we're going to obtain a temperature of 793 degrees Celsius. Okay. So that's what we were asked in the end, in the beginning of the problem, determine the temperature of the strip at the end. Sorry, yes, multiplies, sorry. Sorry about that. There's a multiplication, not a division. I'm sorry about that. Minus 0.001718 multiplied by 300. Perfect. Thank you very much. Any questions on this one? Next one. We're going to go now to move now to unit 6. Okay. We're going to start with 6.11. Just going to grab everything here. I don't have my usual hardware, so I'm trying to make it do with whatever I have here. Just bear with me for a second. I think I have everything. Okay. So we are moving now from unit 4 to unit 6. Okay, I suppose you already covered this unit, haven't you? Just assume that you have. So the upper surface of a 50 centimeter thick solid plate. Let's start taking the data as usual. Let me know if I'm going too fast, if you need more time to copy things, okay? I don't know how long you need, so just let me know if you need more time, okay? The upper surface of 50 centimeters thick, thickness 50 centimeters, so 0.5 meters. Solid plate with a K of 237 watts per meter Kelvin. It's being cooled by water, so this is a cooling process with a temperature, my temperature of the fluid, 20 degrees Celsius. The upper and lower surfaces of the solid plate are maintained at constant temperature of 60 degrees Celsius. So my temperature of surface in the top, 60 degrees Celsius, and my temperature of the surface in the bottom is 120 degrees Celsius. Determine the water convection coefficient and the water temperature gradient at the upper plate surface. Let's start with the convection coefficient, okay? Just some assumptions before we start. In this case, we have no mentions to time or anything, so we are assuming steady state, steady state, sorry. I'm going to assume that my properties are constant again, so I'm not going to need to read the properties again. And I'm going to assume that the heat conduction in the solid is one-dimensional, so I'm assuming one-dimensional system. And there is one important thing here that I'm going to give you the page for you to read after and understand better, but we're going to be assuming a no slip condition. At the plate surface. I believe you already studied about the non-slip condition, okay? If you don't remember, you can refer to page 381, I'm pretty sure. Let me just open here my book. Yes, 381, I even marked it in case you wanted to check it. So here, okay, so page 381, you have a good explanation of the non-slip condition and why we are going to apply the set of equations that we are going to apply, okay? So we are going to be assuming that the convection in the first layer is then the heat transfer in the first layer is due to conduction, and then in the next layer is due to convection. I'm not going to go through the theory, but here is the explanation, the theory, page 381. Okay? Have you studied that with Anthony already? You know, if you don't tell me things, I can't know. I can't participate in the class, you know? Just a second, I got things here back. And my chat back as well. Okay, you have. Thank you. Akmobong. Sorry. Thank you for letting me know. Okay, so again, you can refer to page 381 if you don't remember it, as you already studied it. So we're going to assume the non-slip condition at the plate surface. We already have the thermal conductivity of the solid, but we need the data for the water, okay? So the first thing we're going to do is read the data for water in table A9, okay, at the film temperature. My film temperature in this case, between the top surface and the water, okay, that's what we have most in contact, the water with the top surface. So 60 plus 20 degrees divided by 2. So my film temperature is going to be 40 degrees Celsius, and I'm going to read my properties for the fluid at this film temperature here. I'm going to read my conductivity of the water at the film temperature, 0.631 watts per meter Kelvin. And I'm going to read them. I think that's the only thing that I need to read. Well, as I mentioned, we have a non-slip condition here. Okay? And that implies that my rate of conduction is equal to my rate of convection. Okay. So if I write that, I can say that my conductivity multiplied by temperature of the surface in the bottom minus temperature of my surface in the top divided by the thickness is equal to my heat convection coefficient, temperature of surface 1 minus temperature of the water. What we want to find my H for convection. So I'm going to solve for H. H of convection is equal K divided by L, temperature of surface 2 minus temperature of surface 1 divided by temperature of surface 1 minus temperature of the water. So 237 watts per meter Kelvin divided by my thickness, one thing. Want to know the water convection heat transfer coefficient between the plate and the water, okay? That's why in here I'm using the K of the solid, okay? Just to make it clear which K we are using there. My temperature of the surface 2 minus temperature here divided by temperature 1 minus temperature of the water. So my heat transfer due to convection, my convection coefficient is going to be 711 watts per meter square Kelvin. Okay, questions? First part done. The first part was the convection coefficient between the water and the solid. The second part is asking us to find the water temperature gradient at the upper plate surface. So I want to know how my temperature is changing with, I'm going to assume that is my y, okay? That's my x. So how my temperature change with y. That's what it means by temperature gradient at the upper plate surface. And I want the temperature gradient at the surface of the upper plate. There, okay? So it means that y is equal to 0. Again, going back to our page 381, you are going to find equation 6.4, okay? that tells us that my heat transfer coefficient is equal to minus K of the fluid, attention here, okay? The K of the fluid, my temperature gradient when y is equal to 0, so at the surface, temperature of the surface minus temperature of the water. Sorry about that. We know everything. The only thing we don't know is what we want to find here. So I can solve that for my temperature gradient at the surface, y is equal to 0, is equal minus h divided by k of the fluid, temperature of the surface 1, as the surface is in contact with the water, minus temperature of the water. Minus 711 watts per meter square Kelvin, divided by my K of the fluid, 0.631 watts per meter Kelvin. 60 minus 20 Kelvin or degrees Celsius, either or in this case, it's temperature difference. So my temperature gradient at the surface, y is equal to 0, it's going to be minus 45,071 Kelvin per meters. Okay. Any questions on this one? Yeah, right? The next one is again from Unit 6. I'm going to grab it here. Dot 13. If you have done any of those in class, please just let me know, okay? Let's talk about oranges now. Heisenberg, we read the properties for the water. We read the water conductivity from table A9 at the fume temperature. Start reading, please. The next one. Okay, move on. During air cooling of oranges, so we are talking here, first of all, that our fluid is air. And we have a cooling process. And when you talk about oranges, grapefruits, we are talking about spheres, okay? So it's not a linear system anymore, it's a spheric system now. The heat transfer coefficient for combined convection, radiation, and evaporation. So my heat transfer now is due to convection, and you're told that there is evaporation. Or heat transfer coefficient combines all those things. For air velocities, so this expression that we are going to see is just valid between 0.11 and 0.33. Is determined experimentally and is expressed. So for this range of velocities, I can say that my heat transfer coefficient is equal to 5.05 K of the air multiplied by my Reynolds number, the exponent 1/3 divided by D. Okay? Where the diameter is the characteristic length. My characteristic length is my diameter. Oranges are cooled by refrigerated air at 5 degrees Celsius. So now they're telling me the date of the problem. So my temperature of the air is 5 degrees Celsius at a pressure of 1 atm. That's important for us to read the data for the air. At a velocity 0.3 meters per second. Determine letter A. The initial rate of heat transfer. What is the rate of heat transfer? The Q initial, so at the beginning of the process. From a 7 centimeters give the diameter. Orange initially at temperature of 15 degrees Celsius. My initial surface temperature is 15 degrees Celsius with a thermal conductivity, K of the orange, of 0.5 watts per meter Kelvin. So the first part is a simple part, right? So the first part is just want the heat transfer. Well, let's state our equations here, so it might help a little bit. So our heat transfer rate for conduction is equal H multiplied by area, in this case combined convection conduction, H multiplied by area of the surface, temperature of the surface minus temperature of the air. Okay, well, we don't have the H, we need to find the H. We have the equation for the H here. But we don't have the Reynolds number. So the very first thing we're going to do here is to find my Reynolds number, so I can find my age of convection, so my combined age, so I can find my heat transfer, okay? The first thing we're going to do here is Reynolds number. Well, Reynolds number is equal velocity multiplied diameter divided by my viscosity. We don't have the viscosity. We need to read that for the air, okay? So again, tables. We're going to read that. In this case, it's the fume temperature of the air, okay? So read at temperature of the film. So let's find my film temperature. My film temperature is my 15 plus 5 divided by 2. So my film temperature is 10 degrees Celsius. We are going to go to table A15, okay? And we're going to read the two things from this table. We're going to read the conductivity of the air, 0.02439 watts per meter degrees Celsius, and we're going to read our viscosity, the kinematic viscosity in this case, 1.426 times 10 to the minus 5 meters squared per second. Now I can go back and calculate my Reynolds number. Velocity, 0.3 meters per second. Diameter, dynamic viscosity. Cancel the meters, cancel the seconds. My Reynolds number is going to be 1,472. Okay. Now I know my Reynolds number. I can go back and find my H, my heat transfer coefficient. So my heat transfer coefficient is going to be 5.05 A of the air, Reynolds number 1 divided by 3, all that divided by my diameter. 5.05 multiplied by my K of the air. The K of the air is the one that we read in the table, so 0.02439 multiplied by my Reynolds number, 1,472, exponent 1 divided by 3, all that divided by my diameter. I'm not going to work out the units. I'm going to let that part for you to do at home if you want. So my age of combined convection, radiation, evaporation is going to be 20.01 watts per meter square degrees Celsius. Please let me know if you can't read something that I write or if I'm going too fast, okay? Any questions on that one so far? Oh, sorry. Oh, no. You still have to finish this first part. And now we find the Q, the heat transfer rate. H, the area of the surface, temperature of the surface minus temperature of the my heat transfer coefficient. 20, I'm going to round that to 20, okay? 20 watts per meter square degrees Celsius. My area here, my area is the area of a sphere, okay? So my surface area pi d square, we are considering here the diameter of the surface. So pi d square 0.07 square. Temperature of the surface, thing minus temperature of the air 5. Celsius. So my heat transfer rate is going to be 3.08 watts. Okay. So the first part of the problem we solved that asked us to find the heat transfer rate. The next one asks us to find the value of the initial temperature gradient inside the orange at the surface. So what I want to know now, temperature gradient inside orange at surface. Okay. Again, we go back to our equation 6.4 tells us that when we assume no sleep condition, my convection heat transfer is equal to my conduction heat transfer at the boundary. That implies that minus K delta T divided by delta. In this case, we're going to replace Y by the radius, okay? Because I'm talking here about a circle, a sphere. At my radius equal to the max radius, so at the surface, is equal to heat transfer coefficient, temperature of the surface minus temperature of the air. Okay? Equation 6.4, where my Y is equal to my radius. So my surface, instead of being linear, is according to a radius. What I want to find my change of temperature with radius, so my temperature gradient. So my temperature gradient in relation to my radius, when my radius is equal to the max value, so the surface, is going to be minus age, temperature of the surface minus temperature of the air. One detail here, okay? The K in this case is the K of the orange, okay? Because I want to know my temperature gradient inside the orange at the surface, not my temperature gradient at the air at the surface, okay? So I want to know my temperature gradient at the orange surface. So my K in this case is the K of the orange, not the K of the air. That's going to be equal to minus 20 15 minus 5 divided by my K of the orange, 0.5 watts per meter degrees Celsius. For my temperature gradient is a function of the radius, going to be minus 400 degrees Celsius per meter. Okay. And the last part of the problem asks us to find the Nusselt number, the value of the Nusselt number, our old friend Nusselt number. So our Nusselt number is going to be HD divided by K. Now, okay, when we talk about Nusselt number is related to a fluid, okay? So the K for the Nusselt number is the K for the air, okay? I can't use the K for the solid. The Nusselt number is related to a fluid. So my Nusselt number is going to be 20 watts per meter squared degrees Celsius multiplied by my diameter, 0.07 meters, divided by my K of the air, the one that we read in the table. So my Nusselt number is going to be 57.4. Okay. Any questions on this one? We're going to try to start the last one from Unit 6, and next class we start the ones from Unit 7, okay? So today we covered Units 4 and 6, and then we jump to Unit 6, 7 next class. For part B, you assume the convection heat transfer rate is equal to conduction heat transfer rate at the start. Yes, Connor. So we assume that my convection heat transfer is equal to my conduction. It's not exactly to do with the start, it's to do with the boundary layer. So it's more with the fact that we are assuming a non-sleep condition. So I assume that my first boundary layer here is exchanging heat with the surface by conduction, and the same rate is transferred by convection with the other layers, kind of something like that. Not sure that's the way that Anthony explains, but it has to do with the no-sleep boundary condition. Exactly, exactly, because the non-sleep condition assumes that my velocity at the surface, my velocity at the point where it touches my surface is 0. My velocity of the air at the surface is 0 according to the non-sleep condition. Exactly that. No problem. The next one we're going to start, I don't think we're going to be able to finish this one, is the 6.20. Let me just grab it. Are those exercises helpful, or am I just repeating what Anthony did in class, told you in class? Do you find that helpful? Please let me know. Is it? Okay. One more second, start reading it while I prepare the material. I'm barely going to be able to start, but at least you have, you know what we are starting next week. We are doing next week. So a metal plate, and they are given the data for the metal plate. With a thickness of 1 centimeter. It's cooled by air at 5 degrees Celsius with a convection heat transfer coefficient of 30 watts per meter square Kelvin. If the initial temperature of the plate, temperature of the surface in the beginning of the process, is 300 degrees Celsius, determine the plate temperature gradient at the surface. Plate temperature gradient at the surface after 2 minutes of cooling. Okay. First of all, I say the time, you mentioned the time, a time was mentioned. immediately we jump into transient mode. Okay? When you think about transient, always the same idea. Find the characteristic length, find the Biot number, see if you can apply lumped system. If you can apply the lumped system, we find the value for beam and whatever else we need to do in the lumped system application. In this case, we're going to find my, first of all, my temperature at the surface after 2 minutes. Okay, so you heard the word, you heard the time. There is any mention to change of time, immediately you go into transient mode. Okay, I'm just going to do the characteristic length and the rest to do next week. Okay. Well, first I need to find my characteristic length that tells me that my volume divided by my area of the surface. I know that volume is equal to my thickness multiplied by my area in this case because I have a metal plate. Okay, so it implies that something thin, okay, with two sides. So if it's a metal plate, it's something that is thin and has two sides, same that we did before. So my volume is equal to the thickness multiplied by my area. That's my volume. And my surface area for heat transfer is going to be the sum of the top and the bottom surfaces of the plate. So it's twice my area. Again, my characteristic length is going to be length divided by 2. That's 10 millimeters divided by 2. So my characteristic length is going to be 5 millimeters. Okay. From here, we are going to continue next class, okay? And we are going to finish the application of the lump capacitance method and find the change of temperature. Any questions before we finish the class? Everything all right? Hope that was helpful. I see you in a weekend or in the labs. Okay.